So today we're talking about solution chemistry. There are three types of equations that we're going to be discussing today. They're called the molecular equation, which you actually already know how to do, the complete ionic equation, and the net ionic equation. If you don't have your solubility rules out, you need to take a second and find those because you'll be needing those today. They're on page 108 in your textbook, or you can use the handout that I gave you. Three types of equations. Eqn is just shorthand for equation. Okay? Molecular, complete ionic, and net ionic equation. So what we're doing today is we're going to be breaking down what happens in a solution. When we combine two solutions and something happens, we want to represent that process. Okay? And the way we're going to do that is by looking at three different equations: the molecular, complete ionic, and net ionic equations. So we will look at each one of these. Molecular equation you actually already know how to do. Converting a molecular into a complete ionic is pretty easy. And then converting a complete ionic into a net ionic is pretty easy too. So really today's lecture isn't all that challenging. Yay, right? That's good. First day of the week. Nice soft start to your week. Okay, so let's do this one together. Write molecular, complete ionic, and net ionic equations for the reaction that occurs when solutions of silver 1 nitrate and potassium chloride are mixed. So I want to write all three equations for silver 1 nitrate and potassium chloride. Those two solutions are being mixed. Now the problem tells me that they are solutions. So do I need to use my solubility rules to look up to see if silver 1 nitrate, potassium chloride are soluble? Do I need to look that up for my reactants? Would I need to look that up? No, why not? Why would I not need to look up the reactants? What does the problem state that tells me I don't have to look them up? The problem tells me that they are solutions, right? If it's a solution, then by definition it's soluble, right? So if the problem says occurs when solutions are mixed, then you don't need to look up the solubility of silver 1 nitrate because the problem tells you it's soluble. You don't need to look up the solubility of potassium chloride. The problem tells you it's soluble. Right? But I mean, if you want to confirm that, you can look at your solubility rules. This is soluble, this is soluble. So the first thing we need to do is we need to write the equations for my two reactants. If this step right here that we've been doing since, what, week 2, is still giving you problems, it's seriously time to seek some tutoring. Okay? Come talk to me during office hours, go to tutoring, try the practice problems that I posted online. Okay? If you can't do this step, it's really going to be hard from here on out. So we write our two reactants. Problem tells me it's silver 1 nitrate, potassium chloride, and that they're solutions. That's why the subscripts are AQ, right? Problem tells me that they are solutions. So aqueous is the subscript. Now what kind of reaction is this? Synthesis, decomposition, combustion. What is it? It's double displacement, right? So that means that Ag plus is going to get together with this, or this. Which one is it? Cl minus, right? And K plus is going to get together with NO3. So those two get together, those two get together. And now I do have to use my solubility rules to figure out the state of matter for my products, right? Because the problem doesn't tell me that there's a precipitate or there's not a precipitate. That's up to you to figure out. Right? So you do your double displacement reaction. And then you look at your solubility rules and you see that AgCl is insoluble, right? If you look at your chlorides solubility rules, most chlorides are soluble with the exception of, and Ag plus is listed as one of the exceptions. All nitrates are soluble, so that one's pretty easy. Does everybody see how we got that this one is the precipitate? We did this last week, right, when we were doing stoichiometry and limiting reagent. So hopefully this isn't too difficult, right? Because we've been doing this for at least since last week. We look at the solubility rules to see that AgCl is my precipitate and potassium nitrate is soluble. Okay? So writing the molecular equation, you actually already knew how to do it. You didn't know that you were doing it, but that's what you were doing. Right? You're just writing a molecular equation, meaning that you're looking at the solubility rules to determine what state of matter are the products. Right? So you actually already know how to do the molecular equation. Nothing new there. But now we need to look at our molecular equation. Okay? When you write AgNO3AQ and KClAQ and KNO3AQ, that's not a very accurate way to represent a solution. Why is that? Well, if you look at KNO3, when it's a solution, is the potassium and the nitrate, are they stuck together still? No, the cation and the anion have completely separated, right? When something that's ionic dissolves, remember the intermolecular force here is ion dipole, right? The water completely surrounds the anion with the positive side facing in. The water completely surrounds the cation with the negative side facing in. Do you remember this? Ion dipole intermolecular force is what causes this solution to look like this. All right, so if you write KNO3AQ, that's really not an accurate way to represent the solution because the K plus and the NO3 minus, they're not stuck together anymore, right? They're split apart. So K plus is here by itself, nitrate's here by itself. They're split apart. Same thing here with KCl, right? K plus is here, CO minus is here. They're not touching anymore. They're not linked together, you know, like in a crystal lattice, right? KCl solid would be potassium chloride, potassium chloride, potassium chloride, right? It'd be a repeating crystalline lattice. But when you're looking at aqueous, right, the K plus and the CO minus, they're split apart. And each of these are hydrated. They're surrounded by water molecules. So writing KNO3 or KCl or AgNO3 or KNO3AQ, that's not very accurate. Does everyone see why this isn't an accurate way to represent the solution? Because they're not bonded together, right? They're split apart and they're surrounded by waters. Now this is accurate, right? Because this is just a precipitate sitting at the bottom of the beaker, not doing anything. So that's perfectly fine. But these ones, that's not really an accurate way to represent it. So what we need to do is we need to write what's called the complete ionic equation. So this shows you what's dissolved versus what's not dissolved. Okay? And now we're going to leave our precipitates and our gases alone. If our reaction generates a gas or if our reaction generates a precipitate, we're not going to touch those. We're going to leave them alone. But the complete ionic equation shows us what's dissolved and what's not dissolved. So if this is our molecular equation, right? There's the molecular equation we just wrote. But this is not very accurate. Okay, what does it really look like? It's really Ag plus AQ plus NO3 minus AQ, right? We split this up into its ions because when you dissolve AgNO3, right, if I take a scoop of solid AgNO3, dump it in my water, stir, 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 right? What do I have? I have Ag plus and NO3 minus, right? Aqueous is the subscript, so I've split those up. Same thing here, KClAQ is better represented as K plus AQ plus CO minus AQ. Do we see what I'm talking about here? Right? This is a better representation because they're not touching anymore, right? When they're dissolved, they're completely separated. Now we leave the AgCl alone because it's my precipitate, right? The AgCl just sinks to the bottom of my beaker and I'm not even thinking about it. I'm not going to look at it. I'm not going to do anything about it with this equation, right? It's solid, so don't touch. Our KNO3AQ, well, that's not very accurate. What does it really look like? It's really K plus AQ and NO3 minus AQ. Okay, so this way of representation is more accurate to what's actually happening in my beaker. Okay, the K and the NO3 aren't touching each other. They're split apart. Now here's the big thing. I've harped on you all semester about how when you write formulas for compounds, there are no charges, right? But when you split them up into ions, you get those charges back, okay? You have to put those charges back because this is an ion, that's an ionic compound that is splitting up back into its ions, okay? So if you write Ag, that's not the same thing as Ag plus, right? You have to include that charge. If you wrote K, that would imply that it's potassium metal from the periodic table, very, very reactive. Not the same thing as K plus, okay? So make sure that when you write this as a complete ionic equation, you undo what you've done here, right? This KCl is formed from K plus and CO minus. So make sure that when you split them up, you get the positive and the negative back. Does everyone understand why we leave the AgCl alone? Because it's not dissolved. It's just sitting there as a clump, right? So that's why I say this shows what's dissolved versus what's not dissolved, and we leave any precipitate, or if we formed a gas, if we were doing a reaction that generated a gas, we leave it alone too, right? Because that gas would just bubble out. Yeah?
On the test, are we going to get a copy of the solubility?
Yes, I'll give you the solubility rules. That'll be on your quiz on Friday too.
Okay.
Yes?
So the only time we're ever breaking the equations apart, you're asking for a complete.
Right. Yep. So we'll break them up when we're writing the complete ionic. Now we're looking at this, and you're going, you know, this is pretty redundant, right? This is pretty redundant, because if I'm looking at this equation, I'm going, okay, I've got nitrate on the product side, and I've got the reactant side, and I've got nitrates on the product side, right? So what we're going to do is we're going to clean this up. We're going to clean this up. So nitrate is on both sides, right? If it's just sitting there, and it's just sitting there, right? If I start out as NO3 minus and I end as NO3 minus, have I done anything? No, right? I'm not doing anything. That's not part of the reaction. It's called a spectator. There's another spectator in here. What is it? Someone identify it? K plus, right? It's just sitting there. It's just sitting there. Now, one of the things that you want to use as a self-check to check yourself to make sure that you've done this correctly is if you've done this correctly, the coefficients will match exactly. Okay, so all here, this is all 1 to 1 to 1 to 1 to 1. Are you always going to have 1 to 1 relationships? Of course not, right? So the way that you can check your work is making sure that your coefficients match. That's one of the ways. So K plus isn't doing anything. NO3 minus isn't doing anything. We call them spectators. So they're just floating around in the solution. They're not actually doing any part of the chemistry. Just like if I go watch a basketball game or a football game or a baseball game or a softball game, right? I'm not the one out on the field doing the hard work. I'm sitting in the stands eating nachos, right? I'm a spectator. The winning or losing of the game has nothing to do with me. I'm not doing squat. I'm just eating nachos, right? The person out on the field, the team, they're the ones doing the hard work. I'm just chilling. So same thing here, right? This nitrate and this K plus, they're not actually reacting. They're just floating around in the solution. They're not doing anything. So what you're left with is the net ionic equation. And so that shows what's really happening. So when I combine my two solutions, right? When I combine my two solutions of AgNO3 and KCl, right? The Ag plus from the AgNO3 and the Cl minus from the KCl, those two things reacted to form this precipitate, right? The K plus and the NO3 minus, they're not doing anything. They're just floating around in my beaker, but I'm not doing anything with them. Does this make sense? Does this make sense? So what you're left with is the net ionic equation. No spectators. Does this make sense? Okay, so here are some steps if you like seeing it as a procedure. Right, you're going to write a balanced molecular equation. Make sure that it's balanced. You're going to dissociate everything with an AQ subscript. Right, everything that's solid or gas, we're going to leave it alone, not touching it. We'll remove the spectators, and then we'll write the net ionic equation from everybody that's left. Okay, let's go through a couple of things to watch out for. So this is something that really, really gets a lot of students in trouble. So if this is my molecular equation, calcium chloride plus NaOH, both of these are solutions, they're being combined and I get this precipitate, and then NaCl is also my other product. Let's go through how we would turn this molecular equation into a complete ionic equation. Because my guess is you're probably going to make at least one of these mistakes. Okay, so let's walk through how we would do this. So look at this. The CaCl2 splits up into Ca2 plus 2 Cl minus. Why is there a 2 right here? The subscript is 2, right? There are 2 chlorides for every 1 calcium ion. Okay, so if that subscript is here, it comes out as a coefficient. I see students all the time, they'll write Cl subscript 2 minus. That doesn't exist. Okay? There's either Cl2 the green gas that'll kill you, or there's Cl minus, the ion. Okay, there's no Cl subscript 2 with a charge. Okay, so if that 2 is there, that means that there are 2 chlorides, so I need to represent that as 2 chlorides. What's going to happen when I get to this one? What am I going to do about this coefficient of 2? I have to distribute it, right? I've got to distribute it to the cation and the anion. Right, so that's 2 Na plus 2 OH minus. A lot of students will distribute the 2 to the cation and they'll forget to do it to the anion, just because they see it second and they don't think about it. Right? This one, it's right in front of your face. You're like, oh, okay. But they forget to distribute it to both. Another mistake I see students make a lot is splitting up a polyatomic ion. Right? That doesn't make sense to do. Right? This is a polyatomic ion, so it's not O2 minus and H plus or something crazy like that. Right? It's just OH minus, and there are 2 of them. Do I do anything with this substance? The CaOH2, do I do anything to it? Right, no, it's to precipitate, we just leave it alone. And then when I get to my other product over here, we're going to do the same thing, right? We're going to distribute the 2 to both the cation and the anion. Okay? Now here's where I say your coefficients should match exactly for any spectators. All right, I've got 2 Na on the reactants, and look at that, I've got 2 Na on the products. If I had 1 Na on the product and 2 on the reactant, I'd need to go back and double check. Okay, because they should match if you've uncrisscrossed and distributed all your coefficients correctly. So my chlorides and my sodium ions, they're all spectators. There's my net ionic equation. Okay, this is one of the most common mistakes I see. Either forgetting to bring a subscript out as a coefficient or distributing a coefficient to both substances. Okay, that's a really common mistake, so I want to make sure you don't make it. So it's kind of one of my pet peeves list. Okay, always uncrisscross your formulas, right? So if you want to think about it like this, right, uncrisscrossing. There's no such thing as this. I see this so much. It makes me want to scream. Okay? It doesn't exist. There's no such thing. Cl2 and there's Cl minus. And distribute your coefficients. Look at this one. 2AlCl3 becomes 2Al3. How come it's 6 here? There's a subscript of 3 and a coefficient of 2. Right? So 2 times 3 gives me the 6. Good. And then again, their coefficients should match on your spectators. Okay, so if you have spectator ions, they should match. So if the coefficient's 5 on one side and 1 on the other side, go double check your complete ionic equation and how you got that, okay? You have some kind of self-checks just built in, which is good. Now here's the scenario that happens when both products are soluble. It's called no apparent reaction. So basically what happened here? I took a solution. Remember, a solution is just a homogeneous mixture, right? It's just a solution. I mean, it's just a mixture where the composition is equal, right? And then there's another homogeneous mixture. I combine them, nothing happened, right? Because this product is soluble, this product is soluble. So did anything actually happen? Did anything meaningful happen here? No, I just made a solution, right? Now I've just got Li plus and Br minus and K plus and Cl minus floating around, right? And you can confirm this for yourself, because if you try to write a complete ionic equation, what's going to happen when you cancel your spectators? Everybody's going to cancel, right? So if you are writing your molecular equation and then you're looking at your products and you see, okay, this one's AQ and this one's AQ, you can stop right there and write no apparent reaction. And then make sure you put because both products are soluble. And I want to know that you understand why this is no apparent reaction, okay? I want to know that you understand the difference between a no apparent reaction versus a precipitate forming, okay? So if you stop right here and write no apparent reaction because both products are soluble, then I'm fine. You can go another step and you can do the complete ionic, but I think it'd just be kind of a waste of your time, right? Because everything's going to cancel. You're not going to have a net ionic equation to write. So we call this no apparent reaction. It occurs when both products are soluble. There's nothing happening. You're just making a solution. Bunch of ions floating around. Nothing precipitating out. Nothing meaningful happening. Does this make sense? Okay. So let's do a few practice problems. Write balanced molecular, complete ionic, and net ionic equations for the reaction that occurs when aqueous solutions of silver 1 nitrate and potassium phosphate are mixed. I'm going to pause the recording while you work on that. Let's resume and go over this problem. Okay, so is there going to be a precipitate? First of all, we need to find that out. Because if there's no precipitate, we don't need to spend a whole lot of time writing molecular equation and complete ionic equations, right? Is there a precipitate? Yes, there is. What's the precipitate? Silver 1 phosphate, right? So there's the molecular equation. It must be balanced, right? You've got to balance it, because if you don't balance this, when you split this up into complete ionic equation, your coefficients are going to be a mess, right? So make sure that your molecular equation is balanced so that when you write your complete ionic equation, your coefficients make sense. Do we agree on this part? All right, now we're going to split everything up. Now, if you have to go onto a second row because you've run out of room, that's fine. Just make sure I can follow your work, right? I ran out of space. So just go onto a second row. I understand that you might run out of space on a line. That's okay. Do we understand and agree on how we split these up? Remember never to split apart a polyatomic ion, right? And remember to leave your precipitate alone. All the other substances are going to have AQ as the subscript. And also, if you omit the charges, is that okay? No, that's not okay. Okay, so make sure that you've got those charges in there. Do we agree on the complete ionic equation? What are the spectators? Right, K plus and NO3 minus. Good job. So we cross those out, cleaning things up gives us the complete ionic equation. Gives us the net ionic equation. All right, so this shows us what really happens. Did you get it right? If you made a mistake, you see where you made it. All right, let's do another one. Write the balanced molecular, complete ionic, and net ionic equations for the reaction between aqueous solutions of magnesium chloride and cobalt-2 sulfate. Magnesium chloride and cobalt-2 sulfate. Let's look at the answer to this one. This one is what? No apparent reaction, right? Nope. Both products are soluble, which they are in this case. Right? This is no apparent reaction. So if you wrote no apparent reaction and you wrote your molecular equation and then you wrote because both products are soluble, that's enough to convince me that you know what you're talking about. Okay, so if you just write no apparent reaction because both products are soluble, you can stop right there. So long as you have a balanced molecular equation with subscripts. Okay, if you just write no apparent reaction and don't put anything else, I can't give you credit for that, because remember, your goal is to communicate to me that you know what you're doing. All right, so you need to give me a balanced molecular equation. You'd say no apparent reaction because both products are soluble. I'd be happy. If you took it a step further, which you could, right? You could split this up into all the cations and anions, but what you would find is that everything cancels. So you've just made a new mixture, but nothing happened. Okay, do this one. Write balanced molecular, complete ionic, and net ionic equations for the reaction between aqueous solutions of potassium carbonate and copper 2 iodide. Potassium carbonate, copper 2 iodide. Okay, let's see how this one works out. Do we have a precipitate? Yes, we do. What is the precipitate? Copper 2 carbonate, right? So there's everything all at once, right? We have a precipitate. So there's the molecular, There's the complete ionic. There's the net ionic. Now, if you wrote Cu2 plus CO32 minus, if you switch the order here, would that make a difference? No, right? 1 plus 3 is the same thing as 3 plus 1, right? So long as you have the same cation and the same anion, you're fine. Now, if you write the compound with the cation second, that would be incorrect, right? But in terms of writing them as ions, that makes no difference. Do we feel like we're getting the hang of this? Feel like we're building some confidence on how to do this? I think I've got 2 more for you to do. All right, do this one. I think there are 2 more. Write the molecular, complete ionic, and net ionic equations for the reaction that occurs when aqueous solutions of lead-2 acetate and ammonium dichromate are combined. Lead-2 acetate and ammonium dichromate. Let's see what we have here. We are going to get a precipitate. Do we agree? I mean, when you see dichromate, you should assume that there's going to be a precipitate, because really the only way to get dichromate to be soluble is with ammonium or potassium, lithium, or sodium. Dichromate's pretty picky, so it's going to precipitate out with a lot. So there's the molecular equation. Now, if you wrote acetate as CH3CO2, that's the same thing, right? So you can write acetate as C2H3O2 minus, or you can write it as CH3CO2 minus. Either way is fine by me, okay? So just know that if you wrote acetate as CH3CO2 minus, which is, I think, the way your book lists it in the solubility rules, isn't it? Yep. Okay. So either way works for me. Right. C2H3O2 minus is the same thing as CH3CO2 minus. All right, so lead-2 dichromate is my precipitate. Ammonium acetate is my other product, which is soluble. Right. Now we have a lot to deal with when we write this as a complete ionic equation, because we've got all those subscripts. I always know someone who doesn't know what they're doing when they split up polyatomic ions. Right? If you split up a polyatomic ion, that's a sign to me that you don't know what you're doing. Right? Polyatomic ions stay together. They're a group of atoms with a net charge. So our net ionic equation is lead-2 plus dichromate, producing lead-2 dichromate precipitate. Coefficients all worked out for my 2 spectators, right? Coefficient of 2 for both the ammonium and the acetate. We've got 1 more to do, and then I'm going to show you selective precipitation, just to make sure we're experts at this. Last one. Write balanced molecular, ionic, complete ionic, I should say, and net ionic equations for the reaction that occurs between aqueous solutions of barium chloride and magnesium sulfate. Barium chloride and magnesium sulfate. All right, we do have a precipitate, right? Barium sulfate is the precipitate. Magnesium chloride is soluble. Do we agree? So that means that our net ionic equation is Ba2 plus SO4 2 minus, producing BaSO4. Subscript of the reactants would be AQ, subscript of the products would be S. S for solid. Do we agree on this one? If you made a mistake, do you see where you made it? No. No, I'm just crossing them out on the slide so you can see it more visually. But no, you don't have to cross that out on your paper. If I asked you to list the spectators, though, could you do that? You know, if I said list the spectators, right, you would just list Cl minus and Mg2 plus. But no, you don't have to physically cross it out. Okay, let's talk about selective precipitation. So this is kind of a neat technique. If you've got a mixture of ions and all of them are pretty soluble, you can precipitate them out one at a time if you use your solubility rules. So if you've got your solubility rules handy, now we'll use those. So let's draw kind of a schematic of what that would look like. So let's pretend you've got a solution and it's got X plus and Y plus and Z plus, right? They're all cations and they're all really soluble, right? All these are really, really soluble. Maybe only a couple exceptions. If I add salt number 1, it would precipitate out this as X, let's just say A. Now it's sitting on the bottom as solid, right? Now it's no longer in solution, it's as a precipitate. And now I would add a salt that's insoluble with Y, but not soluble with Z. Or excuse me, you would add a precipitate out Y, right? So it would be insoluble with Y, but soluble with Z. So now this one is, let's just say it was called B. Right? So now it's not as a solution, it's as a precipitate. Then I'd add my third, and then it would be soluble with this one. Let's call it C. You see how this works? If you know the solubility rules, you can look at them and say, okay, I need to pick one that's soluble with this one and this one, but insoluble with this one. That'll get it out of the mix, right? Now I pick something that's soluble with this one, but insoluble with this one. That'll take that one out of the mix. And then I would just need something that's insoluble with this one. Does that make sense? You understand how you're doing this? We're pulling them out one at a time. So here's the example that I give you. A solution contains bromide, fluoride, and sulfate. So these are all anions. How could you separate them one at a time? So look at your solubility rules. Bromide, fluoride, sulfate. Now bromide and fluoride and sulfate are all pretty soluble, right? Because notice they're listed under the soluble compounds section. And then there are only a few exceptions. So there's our solubility rules, right? So if we're precipitating out the bromide, let's start with the bromide. How can I precipitate out bromide but not the fluoride and the sulfate? I want to get rid of bromide but not fluoride and sulfate. So for instance, if I added lead, that would be stupid, right? Because lead will precipitate out the bromide, but it'll also precipitate out the fluoride and the sulfate. So lead's a poor choice because I would get all three of them in one swoop, and I don't want that. So what's something that I could add? Right, I've added mercury, or mercury too, right? I could precipitate out this one. What about here for the fluoride? How could I separate the fluoride and the sulfate? Magnesium would work. What else would work? We've already got rid of the bromide. So could I use Ag plus to separate those two? Ag, oh, yeah, Ag is not soluble. I mean, Ag is soluble with fluoride, but it's not soluble with sulfate. So once you pull one out of the mix, you can then separate the other two. So if I use magnesium to pull out the fluoride, I could use Hg2, 2 plus to precipitate out bromide, Ca2 plus to precipitate out sulfate, right? There are a couple different ways you could do this. So you get rid of one, and then you figure out what I could use to separate the other two that remain. Does this make sense? Yeah.
So once you precipitate one, it can react with.
Right. Once it's precipitated out, if you do your stoichiometry and figure out exactly how much you need to add to get rid of it all, then yeah, there's not going to be any more. So after I've added the magnesium ion, all this fluoride's gone because I'm assuming that I've used my stoichiometry to figure out exactly how much I need to add. So yeah, this one's completely gone, and now I'm just trying to separate those two. Yep. Does this make sense? This is called selective precipitation. And it's a neat lab technique that you can use to separate out ions that are typically pretty soluble. Right? So if you've got ions that are really, really soluble, what are some ways you could separate them? All right, so that's where we're going to stop for today.